Okay, so hello everyone. My name is Antoine Zakardjian. I'm a soon-to-be PhD student at the University of Toulouse, and this presentation is going to be about the impact of H regions on giant molecular clouds in nearby galaxies. So to start off and give a bit of context, the main goal of this work is to study stellar feedback, which is, globally speaking, the input of energy and momentum from giant stars back into the ISM, momentum and energy, which will eventually disrupt the surrounding clouds and molecular gas. So this process is known to be a key process in the evolution of galaxies, without which simulation cannot reproduce the observed properties of galaxies. It's often invoked to explain the low star formation efficiency of molecular clouds, and it's well known that at the final stages of cloud evolution, supernovas are the main cause of stellar feedback and cloud disruption. But it's still not quite clear what is the importance of pre-supernova star feedback or early star feedback, and recent results suggest a significant importance of this early star feedback through radiation, pressure, stellar winds, or photoionization, for example. So with this study, we try to retrieve imprints or empirical evidence of early star feedback by doing a statistical study of a large sample of H2 region and giant molecular clouds. And so by a large sample, I mean that we use a catalog of around 32,000 H2 region from 19 nearby galaxies, catalog which was produced using the PANGS Muse survey of nearby galaxies in H alpha. And on the right figure, you can simply see an emission line map of NGC 628 with overlaid in blue the H2 region mask we used. Now, as for the molecular clouds, we used a catalog of around 11,000 molecular clouds, which was produced using the functional mass surveys of those same 19 galaxies observed in 12CO221. So here on the right, you can simply see the cloud masks in red. Now, there were three main properties that we are interested in. The first one is the H alpha luminosity of H region, because it's a property that somewhat quantifies the energy of H region and which can, disrupt the cloud. And the two other properties are cloud intensive properties that are sensitive to stellar feedback, which is the cloud peak temperature, which, as you probably all know, is simply the maximum brightest temperature of the cloud, and we expect it to be sensitive to heating of the cloud by stellar feedback. The other property is what I will call the cloud normalized versus dispersion, which is simply the cloud line width divided by the square root of the cloud radius, and which should be sensitive to increased turbulence in the clouds due to stellar feedback. Now, the first step in our analysis to study clouds as a function of H region was to somehow associate these clouds in H region. And in order to do this, we used a simple matching method based on the 2D spatial overlap of these clouds and H2 region. So the idea of this matching method is that an H2 region and a molecular cloud are matched if the H2 region covers more than a certain percentage of the cloud, which I will call the minimal overlap percentage. So in this figure, you can see the H2 regions in blue, the molecular clouds in red, and we used a minimal overlap percentage of 10%. So say this H2 region covers more than 10% of this molecular cloud, so the two are matched. Now, if I, for the same field of view and same population of cloud and H2 region, if I get to a minimal overlap percentage of 50%, now only these two pairs of H2 region and molecular clouds are not matched. So with our H2 region and cloud matched, the first step of the analysis was to compare the distribution of cloud properties of the global sample of clouds against the sample of clouds that are matched with an H2 region. So you can see here the probability density function of the peak temperature of the cloud for the all the clouds in red and the matched clouds in blue. And we can see that the matched clouds have a median peak temperature that is higher. There is a global shift of the distribution that we check to be statistically significant. And also this shift increases with the minimal overlap. So when we consider more and more spatially coincident H2 region and clouds, the clouds peak temperature gets higher. Now we can do the same thing for the cloud normalized versus dispersion. So you can see again in red all the sample, in blue the clouds that are matched with an H2 region, and again there is a shift towards higher values, and again this shift with increase with the minimal overlap percentage. So to summarize, the clouds that are coincident with an H2 region have on average a higher peak temperature and a higher normalized versus dispersion, so a higher turbulence. Now the second step of our study was to check the relationship between the cloud properties and the HII luminosity. So here you can see the cloud normalized versus dispersion as a function of the H2 region HII luminosity. And there is here a significant correlation with a correlation coefficient of 0.47. Yeah, the Colloque simply shows the density of points. And now if we look at the peak temperature this time against HII luminosity, there is again a significant correlation. So this is another hint of stellar feedback where the higher the luminosity of the H2 region, the higher the peak temperature and turbulence of the clouds. And it's not shown on the slide, but the steepness and the strength of the correlation we found tend to increase with the minimal overlap percentage, which means that when we consider closer and closer H2 region and clouds, the signal of feedback gets stronger. Now the third and last part of the analysis was to study those global correlation as a function of different galaxies, because we have 19 galaxies in our sample. So here you can see again peak temperature, HII luminosity, considering H2 region and molecular clouds from NGC 1672 only. And this time there is a very strong correlation between the two properties. And now if we look, say, at yes, NGC 1433, there is a very weak, if not negligible correlation, which means that even though globally there is a correlation between cloud properties and HII luminosity, there is a very large variability of this correlation galaxy by galaxy. Now, to conclude this short presentation, I'm just going to summarize the result. So we found that the clouds that are spatially coincident with an H2 region have a higher peak temperature and a higher normalized versus dispersion, which is the first hint of early star feedback. There is also a correlation between the H2 region luminosity and the cloud peak temperature and normalized versus dispersion, which is another, well, empirical evidence of stellar feedback and H2 region injecting energy into the clouds, which raise their turbulence and their peak temperature. And finally, this correlation we found hides a very large variability galaxy by galaxy. And the next step for us would be to select well-chosen pairs of H2 region and GMCs at a better angular resolution to try to enhance the signal we see. And also it would be great to study the clouds in other higher lines than 12CO 2 to 1, because we expect that higher transition line will have an enhanced brightness with increasing HII luminosity. So yeah, this is it for this presentation. Thank you very much for listening.